Hello everyone and welcome back to the course. In this video I will show you how we can generate different random vectors, but for each of these different random vectors we keep the marginal distributions the same. And the idea is that in your modeling you take a two-step approach. In the first step you fix the marginals, in the second step you do the dependence. And of course, if you explore different dependent structures, you want to keep the marginals always the same because you already determined these marginals in step 1. You do not want to deviate from that. So what we assume here is that x1 and x2 are the marginal distribution. So we take a bivariate problem to keep things simple. And assume you have data available to estimate x1 and x2, and you find that a good distribution for x1 is a normal distribution with mean mu1 and variance sigma 1 squared. Similar for x2, you find that x2 has a normal distribution with mean mu2 and variance sigma 2 squared. So that's the information that we have. What we need is we need to determine a random vector. We need to determine x1 and x2. And the problem is that there exist many random vectors that are consistent with this information. We can determine the set with all the random vectors y1, y2, where the marginals of y1, y2, so f y1, corresponds with the marginal distribution fx1, and the same for y2. y2 has the same CDF than x2. So in this set, called this set A, we have all random vectors that have marginal distributions normal with mean mu1 or mu2, variance sigma 1 or sigma 2 squared, but each of the random vectors in A has a different copula. And once we have fixed the marginals, we want to determine different members of A to explore the effect of the dependent structure on our modeling problem. And we will consider two different approaches to see how we can proceed with that, how we can generate different random vectors. We start with method 1. And in method 1, we will focus on Gaussian copula models. It means that instead of looking in the complete set A, we take only a subset of A. So with this method, we can generate different dependent structures. That's good news, but we cannot determine any dependent structure that is in A. So there are vectors in A that we cannot model with this Gaussian copula model. But as a start, let's try this. So what we need is, we need a random vector x1, x2, where the marginals are normally distributed and where we have some dependent structure between x1 and x2. So we start as follows. So call that step 1. Step 1 is we determine the random vector z1, which has a normal distribution with mean 0 and standard deviation 1. And we call such a random variable a standard normal random variable. Then we determine z2 as a linear combination between, on the one hand, z1, and on the other hand, a new random variable, z, where z is also standard normal, and z is independent of z1. So we create two normal random variables, mean 0, variance 1. We call these random variables z1 and z. And using z1 and z, we can create z2 using this parameter rho. So we take a linear combination of z1 and z. And what we can prove is that this rho is the correlation between z1 and z2. Another property of z1 and z2 is that z1 and z2 are both normally distributed. And more specifically, of course, z1 is standard normal distributed by definition. Also, z2 is standard normally distributed. So what we created is a random vector z1, z2, where the marginals are standard normal and the copula is a Gaussian copula. This means that z1, z2 has a bivariate normal distribution. So normal marginals, Gaussian copula. Let's first prove that the correlation between z1 and z2 is exactly rho. By definition, the correlation z1, z2 is given by this expression. Of course, z1 and z2 both are normally distributed with mean 0, variance 1, which means that this is equal to 0 and this here is equal to 1. So we find that the correlation is just the expectation z1, z2. Now, instead of writing z2, we plug in the expression of the previous slide. So we have that z2 is a linear combination between z1 and z. We can now write this expectation as a sum of two expectations. But because z1 and z are independent, also this here is 0. And because z1 has a normal distribution with mean 0 and variance 1, this is equal to 1. So the second moment of z1 is equal to the variance is equal to 1. So we find indeed that the correlation between z1 and z2 is exactly equal to rho. What we did so far is we created the vector z1, z2, where z1, z2 has a Gaussian copula with standard normal marginals. However, we are happy with the fact that we have a dependent structure between z1 and z2 and that we can control the strength of the dependence with the parameter rho. So that's the good news. But z1, z2 has the wrong marginals, because we know that our marginals, x1 and x2, are not standard normal distributed, but they have some mean and some variance. So we need a random vector x1 that we extract from z1, and we take x1 equal to mu1 plus sigma 1 z1, and x2 we define as mu2 plus sigma 2 z2. And then you can prove that the vector x1, x2 has also a Gaussian copula, so it has the same copula as z1, z2, but now it has the correct marginals. It has normally distributed marginals with the correct mean and the correct variance. The approach I explained here starts from the simulation of independent standard normal distributions z and z1. And that is very simple in Excel, in MATLAB, in R. And I will show you after this slide how to do that actually in R. So you just have to simulate twice, z, z1, and you can do that separately because they are independent. Once you have z and z1, you can generate the random vector x1 and x2, where the correlation between x1 and x2 can be controlled by some parameter rho. We start with generating a bivariate normal distribution with a certain mean and a certain variance for the marginals. We assume that the parameters for the first random variable x1 are mu1 and sigma 1. And for the illustration here, I assume that the mu's are 0, the sigmas are equal to 1. But you can change these numbers if you want to have different normal distributions. We use a correlation, which we denote by rho. And here I put the correlation equal to 0.8. So we have a positive dependence. And I will generate 10,000 different samples from this bivariate normal distribution. And remember from the theory I just showed you that we first have to create two independent normal distributions, standard normal distributions. Then we can determine z1, z2, which have correlation 0.8. And then we can scale the z1 and the z2 such that we have x1 and x2 with the correct mean and the correct variance. So I start with generating the two independent normal distributions. I use the function rnorm, which gives you normal distributions, simulations of a normal distribution. This is the number of simulations that I need, and you can add here two extra arguments, which are the mean and the variance. But if I do not fill in anything, the default numbers are mean 0, variance equal to 1. So this generates Z1, Z2 independent standard normal distributions. Then my Z2 is a linear combination of the Z1 and the Z. The Z1 and the Z2 have mean 0, variance 1 and correlation equal to rho, and they are dependent through a Gaussian copula. I can then determine x1 and x2 from Z1, Z2. And then the x1 and the x2 are our normal random variables with the correct mean and the correct variance. I can make a scatter plot to see the dependence between x1 and x2. And then you see here our 10,000 realizations from x1, x2 from a bivariate normal distribution. And to generate x1 and x2 we used a Gaussian copula. Let's now move to a second method. And in the second method, we want to generate a non-Gaussian dependent structure. Assume that we have a random vector y1, y2. And for some reason, we can generate y1, y2, and what we know from y1, y2 is that y1, y2 has different marginals than the marginals that we had for x1 and x2. And it has a different copula, it has a non-Gaussian copula. So a copula that is not a copula that comes from the bivariate normal distribution. It's a more exotic copula. And the thing is that we are actually happy with the fact that it has a non-Gaussian copula, because method 1 allows you to generate dependent structures within the Gaussian copula setting, but it can happen that for your situation it's not sufficient. And you say, well, if we now find a non-Gaussian copula, a new type of dependence, and actually I want to use that copula. The problem is that we cannot directly use y1, y2 because it has the wrong marginals. So y1, y2 is a random vector that kind of for 50% is good to us because it has a copula that we want to use, but we want to get rid of these marginals, and I will show you how you can do that. And what we do is we apply the results of Sklar's theorem. And there were two important results in Sklar's theorem, important formulas I mean. First of all, the joint CDF of the random vector y1, y2 can be expressed as follows. So this is the expression for the joint CDF of the random vector y, and the copula, so the copula that determines the dependent structure, that models the dependent structure of y1, y2, I denote that by Cy. And this copula Cy can be expressed using the joint CDF and the marginals as follows. So in the next slides, I will use these two formulas to show you how I can transform the random vector y1, y2 into a new random vector x1, x2, where x1, x2 has the correct normal marginals, but we keep this non-Gaussian copula Cy. So the problem that we have with the random vector y1, y2 is that the marginals are not the marginals that we need. So we first transform the marginals y1, y2 into new marginals u1, u2. So I define the random vector u1 as I apply the CDF of y1, and for the moment I assume I know what its CDF is, and I assume it's a continuous CDF. So I use the CDF of y1 to go from y1 to u1, and the same for y2. So I apply the CDF of y2 to get the random variable u2. And then using the quantile transform theorem, I find that u1 has a uniform distribution, uniform over 0, 1, and the same for u2. It is also uniform on 0, 1. However, we changed the marginals y1, u1, y2 to u2, but the copula of the random vector u1, u2 is the same copula as the copula between y1 and y2. So I transformed the marginals, but I didn't change anything of the dependence structure. And that is actually a very simple proof. So in order to prove this result, we go as follows. We take the joint probability of the random vector u1, u2. And a copula function is a joint CDF of a vector with uniform marginals. In this case, we transformed the y1, y2 to uniform marginals. So the copula of u1, u2 corresponds with the joint CDF of u1, u2. So that's why I just determined this probability to get the copula, hence the joint CDF. So I replace the u1, u2 with the definitions. Since I assumed that everything is continuous, y1, y2 are all continuous random variables, I can do the following. And here you recognize the joint CDF of the random vector y1, y2. So this is just the joint CDF of y applied in these points. And then you go back to the previous slide to see that this is actually the copula of y applied in u1, u2. And then we see that the joint CDF of u1, u2 is just the copula function of the random vector y, which means that the copula u1, u2 is just the copula cy. So we didn't change anything about the dependence, we only transformed the marginals. In the previous step, we started with the random vector y1, y2, then we removed the marginals by just putting the marginals equal to uniform marginals, but we kept the copula cy. So we get rid of the marginals, we just take the copula. Then in this next step, we will transform the uniforms to the marginals that we actually want. And in our case, we have normal marginals, meaning that we apply the quantile transform theorem using the inverse CDF of the normal distribution. So it means if we start from u1, u2, we define x1 as mu1 plus sigma 1 phi minus 1 u1, because the inverse of x1 is just mu1 plus sigma 1 phi minus 1 p. And you can check that for yourself, that if you have a normal distribution with some mean and some variance, then the inverse CDF of that normal distribution is just based on the inverse of a standard normal distribution. We do the same for x2, mu2 plus sigma 2 phi minus 1 u2. And then x1 has a normal distribution with the correct mean and the correct variance, and the same holds for x2. So we transformed our uniforms to the marginals that we liked, and the copula of u1, u2 was cy, and the copula of x1, x2 is still the copula cy. And on the next slide, I will give a short proof for that. Let's prove that the copula of the random vector x1, x2 is still the copula cy. So we start with this joint probability. Using the definition of x1 and x2, we have that this joint probability can be written as follows. So x1 was equal to fx1 minus 1 u1. And we have the same for x2. So we first defined u1, u2, then we defined x1, x2 in this way. This can be expressed as follows. So I just take the inverse CDF to the other side of the inequality. But this is the joint CDF of u1, u2, and we just proved that u1, u2 has copula cy. So this is the copula function cy, or the joint CDF of u1, u2, applied in fx1, x1, fx2, x2. And then we see that we express the joint CDF, so fx in x1, x2, in this way, which, using the results of Sklar's theorem, means that the copula of the vector x1, x2 is the copula cy. So what we did in method 2, we started with the random vector y1, y2, where the marginals were fy1, fy2, and we had some copula c. Then we got rid of the marginals and we placed it with our favorite marginals, but we kept the copula cy. So this is a way to generate a random vector x1, x2 with normal marginal distributions, but with a copula that is not necessarily a Gaussian copula. And in this case, we take the copula from y1, y2 and use it in our random vector. Let's now generate a multivariate t-distribution. And in order to generate this distribution, I use the library mvt-norm. If you see this library for the first time, you will need to first do install.packages mvt-norm such that this package is installed and you can call it in your R code. With this mvt-norm, we can generate a new random vector. I call this y1, y2, where the marginals have a t-distribution and the copula is a t-copula. So first I determine a correlation matrix where I use the same correlation row as I used for the normal distributions that I had here. So as you can see, I have here a vector 1, row 1, and then I put this vector in a matrix where I have 2 columns and 2 rows and 2 columns. If you check S, then you see that S is a correlation matrix with the variance, which I assume here it's 1, on the diagonal, and here a correlation of 0.8. I can then calculate or determine the multivariate t-distribution, which I put in the matrix Y. So the columns of Y will be, the first column will be Y1, the second column will be Y2, and then I have 10,000 rows, 1 row for each simulation. So RMVT will determine random numbers from a multivariate t-distribution. NSIM is the number of realizations that I need. I assume that the correlation matrix sigma is equal to the matrix S that I defined here. And then I assume that the degrees of freedom that I use for my t-distribution is equal to 3. And then we can see that head Y, so the head command gives the matrix Y, but only the first rows, such that you do not get like all 10,000 rows. Here I see the first 6 rows, and then you see this is the first realization, Y1, Y2. Here we have the second realization, Y1, Y2, and so on. So what I can do now is I can make a scatter plot of x1 and x2 on the one hand and y1, y2 on the other hand. And here you see the results. We have x1 and x2 that I determined in this part, and then I have y1, y2 the random vector that I determined in these lines. And first of all, you can see that there is a difference between the x and the y. But the problem here is that this difference, you don't know if this difference is caused by the marginals, by the dependence, or both. So what we want to do is we want to grab the copula that connects these marginals and use this copula on the marginals x1 and x2. So I want to start from this Gaussian bivariate normal random vector with Gaussian copula. I want to take this copula and plug it into this picture. That's what we want to do. And for example, we can have a look at the marginals of x and y. So what I can do, for example, is I can first take the empirical density of x1. So with the function density, R is calculating the density of the data in x1, and I take the x values against the y values. That gives you the density plot. So this gives you the empirical density of x1. Here you see the density, and we can plot on top of that with the lines argument. I can plot the density of y1. And then you see that we have the blue density is a normal distribution, the red density is the t-distribution, is a distribution that is used in these lines. So then you see that the random vector y has a different dependence, has different marginals compared to the random vector x. And in particular, you see that the red density has heavier lower and heavier upper tails. But what we want is we want to use the blue density, the normal density, but take the copula from this multivariate t-distribution from the y vector. So we want to generate a vector with normal marginals and a t-copula. First step is we change the marginals y to uniform marginals. And I call u1.t the transform marginal of the first y vector in the random vector y. So u1.t is I start from the y1 random variable. I use the distribution function of a t-distribution, so that is pt, that gives you the probability or distribution function of a t-distribution. I have to add the degrees of freedom. We took 3 degrees of freedom. And I do the same for u2, which is the transformed y2 variable. And what we can do is we can compare the histogram, for example, of y1 with u1.t. So y1 is the original marginal of the y vector, u1.t is a transformed one. So with this statement we create two different plots next to each other. So this is the histogram of the original data. This here you see the transformed random variable, where you see that this is indeed looks like a uniform distribution between 0, 1, and everywhere you have the same probability mass, and that is a uniform distribution. And we can also determine the density of u1 to verify it's indeed a uniform distribution, or it approximates at least a uniform distribution. So again, I use this density function, but now I apply it on u1.t. And then you see, of course, outside 0 and 1 the density is 0, and then you see that in between 0 and 1 you have a density that is close to 1, meaning it's a uniform distribution. We can do the same for the x vector. So we have u1.t is I start from the y vector, I move to normal marginals. Now I can start from the x vector and move to uniform marginals. So I determine u1.Gaussian as I start from x1. I apply the distribution function of a normal distribution where I have to say what is the mean and what is the standard deviation. Again, here for u2.Gaussian, I take x2, I take mu2 sigma 2. Again, I can make a plot to see that I transformed from normal distributions to uniform distributions. Here you see the histogram of a normal distribution. Between -3 and 3 you see this bell shape. Here you see again it looks like a uniform distribution between 0 and 1, where everywhere you have the same probability mass. We have created two random vectors. We have the u1.t, u2.t random vector. We have the u1.Gaussian, u2.Gaussian random vector. And they both have uniform marginals, but u1, u2.t random vector has a t-copula, whereas u1.Gaussian, u2.Gaussian has a Gaussian copula. So we can compare these two distributions. And here you see the results. Here you see the t-copula, or simulations from a t-copula. Here you see simulations from a Gaussian copula. And what we have now is we have two scatter plots. We already had two scatter plots when we compared x and y, but then there was this effect of the marginals. Now the marginals in both cases are uniform. So the difference between the two plots only comes from the difference in copula. Here you see a t-copula, here you see a Gaussian copula. And what we want is we want to use this copula, but we want to have normal marginals. So what we need to do is we need to move back from starting from this plot where we have a t-copula uniform marginals. Now we have to move to normal marginals. So we came from t marginals to uniform marginals. Now we have to go from uniform marginals to normal marginals. So I determine x1.c, x2.t as the random vector with a t-copula and normal marginals. I have the t-copula because I plug in u1.t, u2.t. So these were random vectors that already had the correct copula, the t-copula. And now I transform the uniforms to normal marginals using the inverse of a normal distribution, which in R is the q-norm function, where I plug in the numbers of the uniform distribution, a mean and a variance or a standard deviation. What I can do now is I can make a plot of the realizations of x1, x2 and the realization of x1.t, x2.t. And here's the result. So here we have normal random variables with a Gaussian copula. Here we have normal random variables with a t-copula. And you see that by changing the copula, you get different realizations. So changing the copula has an effect on your multivariate problem. And we can check the marginals x1, x2, x1.t, x2.t to verify that we have the correct marginals. So first I have the marginals of x1, x2, and then I have the marginals of x1.t, x2.t. As you can see, all the marginals are normal distributions. So x1, x2 were normal distributions because we created them as normal distributions, as linear combinations of normal distributions, so that was okay. x1.t, x2.t are normal distributed because they come from a uniform where I applied the quantile transform theorem. So let's summarize a bit. We first determined x1, x2, a bivariate normal distribution, meaning normal marginals, Gaussian copula. Then we used the random vector y that had the t-copula to generate x1.t, x2.t. These were again normal distributions, but now with a different copula. So we can go from a Gaussian to a t-copula without changing the marginals, but we take the copula from the y vector. However, when we have the u1, u2 dot t, so the uniforms with a t-copula, we can actually also move to other marginals, because now we said the marginals are normally distributed, so that's why I apply the q norm. But we can say, well, assume I want to have exponential distributions with a t-copula. I know that u1.t, u2.t have the t-copula, so then I can determine my first exponential distribution with a t-copula using the qx function, which is the inverse, the quantile function of an exponential distribution. I use u1.t because u1.t, u2.t have the correct copula, but it's just the marginals. I assume that the rate parameter of the exponential distribution is 1. And then I can do the same for 2. So now I create two random variables x1.t, x2.t, which have exponential marginals but a t-copula. And of course, if I want to have exponential distributions but now with a Gaussian copula, I can do that too, because I have uniforms that have the right copula. And now we can compare these two different distributions. And what we see here is a random vector with exponential distributions with a Gaussian copula, and here we see exponential distributions with a t-copula. And again, by changing the copula, keeping the marginals the same, we find different multivariate distributions, different multivariate models. And that is that was the goal of this exercise here, is to first see how we can generate different multivariate models by changing the copula, and also by seeing that this has an effect. So you want to explore more copulas. Maybe there are other multivariate distributions that have interesting copulas, meaning copulas with properties that maybe you want for your application, but you cannot use a Gaussian or a t-copula. Then you want to use another copula. So if you find such a copula, you can use this approach to generate realizations of this copula.